Welcome back to Hansen Theory. Up to this point, you have learned molecular forces, Hansen space, Ra distance, red number, polymer behavior, solvent blend design, pigment-resin interactions, and cross-linking and curing interactions. Now we move into the practical heart of coatings engineering, predictive troubleshooting. This is where Hansen Theory shifts from being a theoretical tool to a real-world decision-making framework. Many engineers wait until problems appear before acting. Minority-thinking engineers anticipate issues before they occur. They use molecular insight to prevent defects rather than react to them. This is the difference between a reactive approach and a predictive approach. Let's begin with the first step, understanding the system as a molecular network. Every coating formulation is a network of interactions. Polymer chains interacting with solvents. Polymers interacting with pigments. Solvents interacting with additives. Reactive groups interacting during curing. Each interaction can be represented in Hansen space. Every point in this space represents a balance of dispersion, polar, and hydrogen bonding forces. Ra distance and red numbers quantify the compatibility between components. Predictive troubleshooting starts by mapping your formulation in this space. If a coating shows defects such as haze, settling, poor gloss, or inadequate curing, the first question is not, which ingredient is wrong? The first question is, which interaction has shifted outside the solubility sphere? Let's take a classic example, pigment flocculation. A titanium dioxide-containing coating suddenly shows uneven dispersion. By mapping the pigment's surface properties, the resin's polymer chains, and the solvent blend in Hansen space, you can see the effective Ra distance increased. Maybe the solvent evaporation rate shifted during mixing. Maybe a dispersant was insufficient or incompatible. Maybe temperature changes reduced molecular mobility. The problem is no longer a mystery. It is a distance problem in molecular space. Next, consider incomplete curing. The film is soft or tacky after drying. Instead of guessing, you calculate Ra between the polymer's reactive sites and the curing agent. Maybe a solvent evaporated too quickly, increasing red above 1 for critical interactions. Maybe the polymer chains are too rigid at room temperature to allow effective contact with cross-linkers. By understanding which molecular forces are misaligned, corrective action can be targeted, adjusting solvent blends, temperature, or additive levels. Now, consider phase separation. In multi-polymer systems, two resins may appear compatible individually but separate during drying. Plotting their points in Hansen space often reveals that their interaction distance exceeds acceptable limits. By adding co-solvents or compatible additives, you can shift the effective Ra distance and bring red below 1, restoring stability. Next, temperature and environmental changes. Scale up from lab to production often introduces shifts in red values. Heat, humidity, and shear affect molecular mobility, solvent evaporation, and polymer-solvent interactions. Predictive troubleshooting anticipates these shifts. You do not wait for the batch to fail. You calculate where the formulation will sit under production conditions and adjust parameters proactively. Minority-thinking engineers also use sensitivity analysis. They test how small variations in solvent ratios, pigment grades, or polymer molecular weight affect Ra and red. This identifies critical factors that could cause failure. They reinforce robustness by optimizing formulations to tolerate expected variations. Now, let's discuss additive interactions. Additives like dispersants, surfactants, stabilizers, and catalysts can dramatically influence red values. Predictive troubleshooting considers how each additive affects molecular alignment. Blind addition can reduce compatibility, even when primary ingredients are ideal. Consider another example, waterborne coatings. Water-based systems introduce additional variables, hydrogen bonding with water, ionic interactions, and evaporation rate differences. Predictive troubleshooting in these systems requires plotting polymers, solvents, and co-solvents in Hansen space and evaluating red for all critical interactions. Next, connecting predictive troubleshooting to pigments and fillers. Pigment flocculation, settling, or floating often correlates with increased Ra distance or red 1 between pigment surfaces and resin. Additives and co-solvents are not random. They are tools to reposition the effective interaction point inside the solubility sphere. Now, let's address common industry mistakes. Waiting for defects to appear, reactive approaches are inefficient. Changing one ingredient blindly, without understanding RA and red shifts, changes may worsen stability. Ignoring polymer molecular weight and functionality, these factors amplify or reduce interaction forces. Neglecting environmental effects, temperature, humidity, and shear can alter red in real time. Predictive troubleshooting avoids all of these mistakes. Stepwise approach. Map all formulation components in Hansen Space. Calculate RA distance and red numbers for critical interactions. Identify interactions outside the solubility sphere. Determine which variables can be adjusted: solvents, additives, temperature, ratios. Implement changes systematically. Monitor red dynamically during processing and curing. By following this method, engineers move from trial and error to data-driven, molecular-level decisions. Now, let's discuss monitoring and feedback. Even with perfect initial design, production and environmental variation can shift red. Minority-thinking engineers track key indicators: solvent composition, temperature, viscosity, and predict red shifts in real time. This allows early intervention before defects occur. Finally, predictive troubleshooting is not just about fixing problems. It is about designing systems that are inherently robust. Solvent blends aligned to polymer and pigment. Additives selected to reduce RA distance. Red maintained, one throughout process, and environmental variation. Curing optimized for molecular accessibility. Polymer networks balanced for performance and stability. This mindset transforms coatings R&D. Formulations are no longer recipes. They are engineered systems with predictable behavior. In the next episode, we will explore advanced multi-component formulation optimization, connecting all Hansen Theory principles to complex, real-world coating systems. If you want to predict and prevent coating failures instead of reacting to them, continue with this series. This is Hansen Theory.